Hello, I am Dr. Abhishek Sharma. In this video, I will discuss the digital modulation technique, frequency shift keying. So let us start. Digital modulation frequency shift keying. As I have already discussed in the previous videos, the bandpass digital modulation means there should be an involvement of carrier frequency to transmit your digital data from transmitter end to receiver end. That means in bandpass digital modulation methodology, whatever modulation methodology you are using at the transmission end, you transmit your signal with the help of antenna. That means you are using electromagnetic high frequency signal, that is your carrier frequency, to transmit your digital data by changing any property. Like for example, if you are changing the amplitude of the carrier with the help of your digital data, that means you are considering the amplitude shift keying. Now in this video, as I am going to discuss frequency shift keying, that means I am changing one property, which is the frequency of the carrier, with the help of the digital bit stream. So that means at the receiving end, I am just receiving the signal, right, with the help of the antenna. That means I am considering the frequency shift keying as a band pass digital modulation, because I am using the carrier frequency to transmit our bit stream from one point to another. Now, what is the representation of frequency shift keying? That means in this type of modulation methodology, the digital data stream changes the frequency of the carrier. Let us suppose if FC is your carrier, that means if you are transmitting 1, then you will send the frequency F1. It may be FC plus delta F or something else frequency, which is actually the integer function of your carrier frequency maybe. And that means for example, if you are sending, let us suppose F1, I am just considering F1 Hertz, right, and 0 will be transmitted by another frequency, which is F2. That frequency have also relation with FC, that means FC minus delta F for F2, that is the lower frequency contained, and higher frequency will be considered as FC plus delta F. In this pictorial presentation of frequency shift keying, you can clearly see that F1 is the frequency which is I am just transmitting our bit stream 1 bit, right? So you can see that, and the difference between the 1 and 0 representation of frequency, that let us suppose this is F2, then F2 is your FC minus of delta F, as I have already shown this in the previous slide, and this will be F1, that will be equal to FC plus of delta F. You can clearly see that the number of oscillations in this section is higher in comparison of oscillations in this sections, right? So this is TB, that is the bit duration for 1, and again if I am transmitting the binary frequency shifting, that means I am using already I am using 1 bit to transmit the digital data. So the duration of 1 and 0 in this pictorial presentation is same, that means TB and TB. So whenever you transmit your 1, it will be transmitted as F1 frequency. That means you are transmitting your signal as cos 2 pi F1t, right? So if you are transmitting 0, that means you are transmitting cos of 2 pi F2t, right? So this is the simple presentation of digital frequency shift keying. That means you are transmitting your carrier, but there are two different carriers with different frequency contained. And how many number of frequencies? 2, because you are transmitting your binary signal only, right? So that's why 2 frequencies are here. So this is the pictorial representation of the bandwidth of frequency shift keying. You can clearly see that as the 2 carrier frequencies are simultaneously transmitted. That means F1 and F2, these are the two frequencies, and the gap will be 2dF, right? So it is the you can, as in the previous picture I have, if you consider the difference between the F2 and F1, you will find that 2 delta F, right? So here 2 delta F is 2, actually this is 2 delta F, 2 dF means 2 delta F. It is, so the total bandwidth breakup, that means actually you can clearly see that if you consider this one band and this one band, you can clearly see that I am transmitting 2 digital binary amplitude shift keying signals. That means I am just combining 2 different frequencies ASK signal and transmit these 2 different ASK signals simultaneously in one medium at once or single instant of time. So you can clearly see this in this pictorial presentation of bandwidth, that these 2 different ASK signals is transmitting into the channel at the same instant of time. So FSK, especially BFSK, will be considered as BASK plus BASK, right? So how can we do that? I will describe it in further slides. Now, if the difference between the two different frequencies f1 and f2 is 2 delta f, then the required bandwidth B, as I have already discussed, B will be given by 1 plus D into S plus 2 delta f. Now, consider an example. We have an available bandwidth of 100 kHz, which spans from 200 to 300 kHz. What should be the carrier frequency and the bit rate of if we modulate our data using FSK with D equal to 1, right? So this problem is similar to the previous example, right? So, but we are modulating by using of FSK. So we will use this formula with the help of this by putting all the values which is available in the question. You can clearly find out the number, the bit rate, which is 25 kbps, as well as the baud rate, right? Because you are transmitting D equal to 1. That means one symbol contains one bit. That means the baud rate and the bit rate will be equal. Now, as per the demodulation methodology for binary frequency shift keying, the demodulation methodology will be divided into two different types. One is coherent and another is non-coherent. It is same as described in the previous videos of binary amplitude shift keying. As binary, as I have already discussed, that BFSK can be considered as 2 BASK at same instant of time. So as BSK can be demodulated in two ways, one is coherent and another is non-coherent. So in the same way, I will also demodulate the frequency shift keying in two manners, right? One is coherent and second one is non-coherent. Right? In non-coherent FSK scheme, when we change actually from one frequency to other, we do not adhere to the current phase of the signal, right? So if phase is not an issue, then you can consider the non-coherent. Otherwise, you will use coherent FSK, which is the switch from one frequency signal to another frequency. Only occurs at the same phase in the signal. So there are some limitations for coherent FSK. One is that your frequency deviations should be 0. As well as the phase deviation should not be equal to pi by 2, right? So that actually when you consider the phase as pi by 2, you will obtain a problem that is considered quadrature null effect. Now there will be also possibility of multi-level FSK, in which you transmit number of symbols, and one symbol is considered as number of bits n, let us suppose. So L, total number of symbols will become 2 to the power n. When you consider more than one bit in a symbol, then you will definitely adhere with multi-level FSK. So similar to ASK, FSK can be used multiple bits per signal element. That's why I'm talking about the symbol. This is symbol, right? Symbol. That means we need to provision for multiple frequencies, each one to represent a group of data bits, right? So this is MFSK. I will describe it in the next section. And after MFSK, you will see that you have to use the voltage controlled oscillator for this purpose. Another example, we need to send data, let us suppose 3 bits at a time at a bit rate of 3 Mbps and the carrier frequency is 10 MHz. Calculate the number of levels, right? Number of levels means L is equal to 2 to the power n, right? So as 3 bits are there, the total number of levels will be 8, right? So the baud rate will be 3, right? Because you are combining 3 bits, right? 3 Mbps divided by 3, as the bit rate is 3, so the baud rate will be total. When you will divide the bit rate divided by the number of bits in a symbol, so you will get the baud rate. So that will be 1 m baud, right? This means that the carrier frequency must be 1 MHz apart, 2 delta f, right? So the bandwidth is B is equal to 8 into 1, and so that is equal to 8 MHz. That figure actually, this one is the figure, shows the allocation of frequencies and the bandwidth, right? So this is the figure, and these are the megahertz, which is actually hidden in my picture. So this is 6.5 megahertz, 7.5 megahertz, 8.5 megahertz, and so on. So this is the actual carrier frequency, and the total bandwidth is of 8 megahertz. Now come to the modulator part of frequency shift keying. As I have already discussed, that FSK can be considered as 2 binary amplitude shift keying. So how can we do that? This is very simple. You will take, let us suppose that you have to transmit 2 frequencies. That means if I am talking about 1, I am transmitting F1 signal, right? If I am talking about 0, then I am transmitting F2 signal, right? That means frequency F2 and frequency F1. So that means I have to transmit cos of 2 pi F1 electromagnetic signal with the frequency F1 and cos of 2 pi F2 electromagnetic signal with the frequency F2. So how can we do that? This is very simple. So let us suppose this is our unipolar data. Let us suppose this is unipolar data stream, right? So unipolar data stream means you are representing your 1 with plus 1 volt, and 0 will be represented by plus of 0 volt. right? This is unipolar NRZ bit stream, right? Once you you will, for example, you have to let us suppose this is your 1, this is your 0. If you have to transmit, that means from here you will transmit cos of 2 pi f1t, and for 0 you will transmit cos of 2 pi f2t, right? So for this purpose you have to invert your 1s to 0s and 0s to 1s. For example, when you will transmit, for example, this is your simple data, and you will multiply carrier signal cos of 2 pi f1t, right? So when you multiply this, you will get BASK. That means you will get, for positive ones you will get cos 2 pi f1t signal. Similarly, for example, if you invert your unipolar data stream with the help of an inverter, then after that if you multiply this with another frequency cos of 2 pi f2t, you will get another BASK, and after that you will combine these two signals and you will finally get cos of 2 pi f1t plus cos of 2 pi f2t. Now point is, how can we see these two signals at the same instant of time? For example, let us suppose this is 1 and this is 0, right? So once you create BASK, so you will get like this, one signal and after that 0. And for second one where you invert this signal, so when you invert this signal, your 0 will become 1. So let us suppose this is 1, this is 0. So when you invert this signal, right, so you will get 0, your 1 will become 0 and your 0 will become 1, right? So when you multiplied again your data bit stream with the another electromagnetic frequency cos 2 pi f2, so you will get 0 here, and you will get at this point you will get this one. So this is cos of 2 pi f2t. Now the point to be noted that at any instant of time you will only get one signal. For example, for this duration you will transmit only cos 2 pi f1t, and for this duration you will transmit cos 2 pi f2t. So if you add these two different signals, so you will get, for example, this one is your 1, this was for your 1, and for 0 you will definitely get another signal like this. So this is this one and this part is this one. So this is the way how FSK technically generated with the help of the modulator. In this diagram you can clearly see that your binary data bit stream is transmitted to two different balanced modulators, but in second one you can clearly see that there is an inverter present at the in front end of the balanced modulator. So for one balanced modulator you can clearly see that cos 2 pi f1t signal is present, and for the second balanced digital modulator you will see that cos 2 pi f2t is here. So after that you will combine these two signals with the help of a summer, that is summation. This is the plus symbol for FSK signal like this. So this is the modulator. So now come to the next point, which is the demodulator. As I have already discussed that demodulator will be of two types, coherent and non-coherent. That will depend upon the demodulation methodologies. So in this figure you can clearly see that this is a local oscillator. This L1 is a L1. If you, let us suppose if you want to extract a cos 2 pi f1t, that you have to use a local oscillator with the frequency cos 2 pi f1t, and if you have to recover, actually what will happen that there are two signals, cos 2 pi f1t and plus cos of 2 pi f2t, right? So these are two different frequencies. For example, if you have to extract the data from this cos 2 pi f1t, you have to multiply with the same frequency at the receiver end. So let us suppose that A is the data and B is the single data here. Then what will happen that when you multiply cos 2 pi f1t with this composite signal, this will become higher frequency content, and when you multiply two carrier frequency like cosine and cosine or cosine or sine, there will be two frequencies. After that, one is positive, subtraction, addition, and another is subtraction. One is addition, second one is subtraction. So the addition, you can say the addition frequencies will be suppressed by the low pass filter, and the subtracted frequencies will be passed out from the low pass filter. So if I am talking about the cos 2 pi f1t, point to be noted that from when you multiply this low frequency obtained from the local oscillator with this signal, you will only get A at the output, right? And this is 1 because I have used cos 2 pi f1t for 1. Similarly, for L2, that means if I am talking about cos 2 pi f2, this is pi cos 2 pi f2t, then B will be associated as B is your data 0. So B will be actually extracted with the help of the band pass filter. Actually, this is the correlator, which is actually sampler and an LPF. So this is the pictorial presentation of these two terms. As I have already discussed, this is the match correlator is your match filter. So this is the match filter. Actually, I have already discussed in the previous videos of ASK that you need to, when you want to extract the digital bit stream at the receiving end, you have to sample the continuous signal at t equal to TB, let us suppose, which is the bit duration, and after that you have to pass that data with the LPF and then decision circuit. So you can clearly see that this is the actually from that point to this point the arrangement is same, but because of the modulation specification, which is the frequency, I have to use two different local oscillator at the front end of these circuit, that is band pass filter, right? So this is the coherent demodulation. Why this is coherent? Because I am using local oscillator at the receiving end. Now there is another demodulation methodology which is non-coherent. So you can clearly see that in non-coherent detection you cannot find any local oscillator here. I am not generating any carrier frequencies, right? Any carrier frequency at the receiving end from any local oscillator, right? So you have to just receive the signal and filter or match filter to that particular symbol, right? If you are transmitting F1 2 pi F1t, then you have to match with 2 pi F1t. Basically, actually, if you consider these 2 points, you can clearly see that you have to use a diode. You can also use a half wave rectifier for this, and at this point you can also use half wave rectifier. And then after that, you can clearly see that this is the envelope detector, right? I am just talking about these terms. So this is envelope detector. When you use envelope detector for the demodulation purpose, so it will be considered as non-coherent demodulation for FSK, frequency shift keying. And after that the procedure will be same, that means sampler, right, and an LPF which is missing here. LPF, you can also use LPF, and after that a comparator is required to detect the output, either it will be a 1 or a 0. So these are the two demodulation methodologies, coherent and non-coherent. Now the point is the coherent demodulation methodologies, it is actually in comparison of non-coherent, it is not cheaper, it is actually costlier because of the synchronization circuitry used at the receiver end. Because as I have already told you, when you use the local oscillator, the frequency difference, that means incoming signal and the generated signal from local oscillator, the difference should be 0, as well as your difference, that means your phase difference should not be equal to pi by 2, otherwise you will get a quadrature nullified. So that's why this is so crucial, and so timing circuitry is very important. But in non-coherent case it is cheaper, but your output is not as clear or specific as you received in coherent. So there are some pros and cons for these coherent and non-coherent. So this is the frequency shift keying in this video. So thanks a lot.